Welcome to this session. This is our technical panel session number 2 for power and energy in this NEECECON 2024 and ASTICON 2024. So for our first presentation, this will be delivered by one of our faculty members from EEEI, who has just earned his PhD from Japan, Charleston Ambatali. His presentation is on dynamic beam focusing techniques in long-range wireless power transfer. Can we flash this slide on the screen, please? Thank you. There. And if I may read the abstract as he prepares for his presentation. Dynamic beam focusing techniques in long-range wireless power transfer by Charleston Ambatali. Long-range wireless power transfer is envisioned to have large antenna arrays from having millions of elements in ground-based applications to billions of elements in space-based applications. A challenge to build this technology is the need for precise control over the amplitude and phase of all the elements for successful and efficient power transfer. Moreover, the individual antennas must also cooperate to compensate for any changes in the propagation environment, such as but not limited to the movement of the receivers, passing obstruction, and changes in the atmosphere. Different techniques have been developed to maintain an efficient transmission in the presence of aforementioned stochastic effects, such as dynamic beam focusing techniques. Currently, the development of these techniques can be classified into 3 types. First, use of classical beamforming with position tracking sensors. Second, use of pilot signals to train the beamforming antenna. And third, the use of telemetry data as a feedback mechanism. This presentation by Charleston will give an overview, comparison, and contrast of these research works. The analysis of their steady-state wireless power transmission efficiency will also be discussed. So let's give a warm welcome to Charleston.
Okay, so hello. So good afternoon, everyone. So once again, my name is Charleston. So my background is not really about electrical grids, electrical engineering. So my background is more on microwave theory, radio frequency engineering. So why am I presenting here in this session of power and energy? Okay, so I'll give you an outline of my presentation. It's divided into 5 parts. I'll give you why am I part of this session, and how do we calculate efficiency in this long-range wireless power transfer? What are the dynamic beam focusing techniques, which is the focus of this presentation, some performance comparison via simulation, and a summary of this presentation. Okay, so first, why long-range wireless power transfer? The motivation is really because of space-based solar power. So what it is you collect solar energy from space and beam it down back to Earth in a focused beam. So the beam focusing here is at microwave frequency. It's a very large structure. So if you want a 90% efficiency, beam collection efficiency, your satellite at geostationary orbit is by around 2.5 kilometers by 2.5 kilometers in size. So that's 1 billion antenna elements that you need to control. And this size is estimated to supply 1.6 gigawatts of power. Okay, so this is an overview of its different subsystems, and what I want to focus here is the DC to microwave block and the rectenna block, at least the interface between them. How do we transfer power from a long distance? Okay, so just a review. So when you talk about electromagnetic wave propagation, you can roughly divide it into 3 zones. The far field, where communication systems happen. The reactive near field, where we do some circuit theory approximations. In between them is called the radiative near field, where long-range wireless power transfer is envisioned to operate. So that is the focus of this of the long-range wireless power transfer technologies. So it is dependent on the frequency of operation or the wavelength of operation and the size of the antenna. So the bigger your antenna, the longer distance you're able to transmit. The larger distance is your radiative near field zone. Okay? So the challenge of implementing this is that if you have a big antenna, you subdivide it into antenna elements. And you have to control the amplitude and phase of each antenna element to focus power towards a specific area in the radiative near field zone. Okay, so at geostationary orbit, that's at least 1.5 billion antennas. So what can be an appropriate beam control method for this scale? So before we go there, let's look at how we compute for the wireless power transfer efficiency. Okay, so this is the framework that we use to calculate the efficiency of wireless power transfer. So we base it on what we call scattering parameters. Because we're dealing with waves, we use the scattering parameters to characterize the wireless power transfer. So what it is at each antenna, you have a voltage that you measure. You can decompose it into its forward component and backward component. And you can relate these components using the S parameters. Okay, so the matrix equation there is the relationship between your backscattering and the input to your channel. Okay, so this is just for 2 antennas. We can extend this concept to multiple antennas. So it's a big system already. So there's one side is the receiver, some parts of it is free space, one side is a generator, other parts of it is the free space, and you can ultimately form this big matrix to relate the received energy and the energy you put in the system. And quite simply, the efficiency is just, if you have the voltage vector of, you measure at your port 1B here, and you transmit power using V2F, the efficiency is what you see here. And simplifying it further based on S parameters, we get this box expression, which is also the Rayleigh quotient, as we call it. So this Rayleigh quotient can be found in quantum physics, this formulation. And the maximum value, the optimum value of this is the maximum eigenvalue of the matrix that you see here, which is defined by your channel. So this S21, Hermitian S21, is dependent on your antennas, the characteristics of your channel, and all of that. It factors everything into this, this matrix right here. Okay, so if we're talking about eigenvalues, we have eigenvectors. So eigenvectors, we have transmission modes that we can define, and there's one eigenvector that maximizes the wireless power transfer efficiency. Okay, so now let's look at the techniques developed to achieve this or to find this maximum eigenvalue condition. So one technique is you just detect your receiver using a sensor. It could be a camera, or your receiver could have a GPS sensor, and it reports its position. And your controller just computes using classical beamforming computations to point the beam towards the receiver. Another approach is you release a pilot signal from your receiver, and your transmitter, your power generator, will train itself to point towards the receiver. And the last approach is you use your telemetry. You send back some data, maybe the power you receive, and then you optimize the beam based on the data that you get. Okay, so those are the three broad approaches towards wireless power transfer. Okay, so these are the summary of all the works that we've reviewed for the different methods. So what type are they? Basically, you can see here that there's a trade-off between your feedback, your settling time, how fast your system settles, compared to achieving the maximum possible efficiency. So if you want to be fast, it's going to be hard to achieve maximum possible efficiency. But if you have enough time to adjust, you're able to transmit in the maximum efficiency mode. Okay? So let's have some performance comparison. Okay, so what we did is we simulated a moving antennas or a moving obstruction in an electromagnetic simulator. Okay, so the first one is the antenna is revolving around the other. The second one is there's an obstruction passing through the space between the two antennas. Okay, so this is a scaled version of this long-range wireless power transfer. It's still in the radiative near field, rather. So you compute the S parameters for each case and then incorporate it in a time domain simulation. So this is the block diagram we implemented in Simulink. So we are able to model the S parameters, the wireless channel, based on the electromagnetic simulation results. Okay, so basically, the S parameters just define a gain and a phase delay, or a time delay, to each of your inputs, and then you just sum them towards your receiver. So this is the time domain model. Okay? So first, we simulated the case where the channel is not moving, but the antennas are misaligned, okay, and measured the settling time and the steady state efficiency of each of the different types of wireless power transfer techniques, beamforming techniques rather. So as I've asserted earlier, the position tracking type and the pilot signal, or the pilot signal beam training type, can settle very fast. In this case, compared to the others, it settles at 0.06 microseconds. If you're going to use some feedback-based methods where you iterate over different data, maybe you will be slower, maybe 2.56 microseconds at the worst. Okay, but when you look at the efficiency, all the feedback-based methods are able to achieve the maximum possible efficiency afforded by the channel condition. Okay? So the trade-off that we asserted earlier is observed in this simulation results. So what happens now if we put it in dynamic channels? So when the channel is moving, the maximum efficiency also changes over time. Okay, so for the first case on your left, this is the revolving antenna case. It is maximum when the antennas are in the best alignment case. So as you can see here, from the worst alignment, it revolves towards the best alignment case. And you can see that the efficiency of all cases increases. That's the graph on the upper left. So the lower left graph is just the ratio of the efficiency with the theoretical maximum. If you look at the graphs, you can see that for the position tracking type and the pilot signal type, they're not able to achieve maximum efficiency in most of the cases. But for the iterative types or the feedback-based types, you're able to see that it can achieve the maximum possible efficiency in that case. Same is what happens when there's a passing obstruction. So what happens here is that initially there's no obstruction. So this is the graph on your upper right. Initially there is no obstruction, and then it passes through until it's completely in the middle. So when there's an obstruction, you can see a decrease in efficiency. Okay, and then if you look at all the cases of all the different types of beamforming techniques, it's still the same. Okay, so what happens is the feedback-based types are able to achieve maximum efficiency that is afforded by the channel conditions at that time, okay, compared to your position tracking type and your pilot signal type. Okay? So to summarize this presentation, okay, so if you want to transmit in long range, you need a large antenna composed of small antenna elements, and you must be able to control them. Okay? So we introduced 3 broad types of techniques to control the beam, and we observe a trade-off between trying to achieve maximum efficiency afforded by the channel and the settling time. So the slower you are, the more you're able to achieve maximum efficiency. Okay? So some future works. So now next is to how do we improve the efficiency? So in this study, we only focused on the channel conditions, but there are techniques to increase the efficiency by improving your antenna design. Okay? And also there's also to implement a stabilization in one of the feedback-based types, and possibly to go smaller first, not space-based. So go smaller first and do it in applications like mobile charging or EV charging. So yes, that's the end of my presentation. So any questions?
Sige, Charles, kung wala pa silang tanong, where can they read your articles pagkatapos itong session na ito? Search na lang kami ng...
So you can actually read some publications that we made for this, for all of these studies. you can look at my Google Scholar page. It's nandun halos lahat. Yung mga recent publications ko from 2022 to 2024. So a lot of it is published. Yun din yung pinresent ko dito halos.
Thank you, Charleston. Kulang yung 15 minutes para sa Sir PJ ko sa question over there.
One question, Charleston. Thank you for the presentation. So, yung minention mo kanina na 1.5 billion antennas, no? And it's supposed to be in the near field, radiating near field.
Yes.
Ano yung, para makuha yung size na yun ng array, anong orbit yung ina-assume dito?
So, ina-assume namin na yung orbit is at 36,000 kilometers elevation at 5.8 gigahertz. So it's at half wavelength spacing yung antennas. So you're able to get at least 1.5 billion antennas. Yes. I remember correctly, yes.
Sige, usap na tayo mamaya. Thank you.
Thank you, PJ. Kasi doon sabi ko yun, kulang yung oras para i-discuss ito nga ito. We actually invite you to join the graduate program sa EEE, magiging teacher niyo si Charleston. Because before you go down, we give him this certificate of appreciation, which you present to Charleston. Charleston Ambatali for sharing his insight and work on dynamic beam focusing techniques in long-range wireless power transfer during NEECECON 2024, given this 18th day of July, signed by Dr. Lutria, Director of EEEI. Thank you. In the interest of time, I won't be reading the abstracts for the next presentations. But the next one coming up will be delivered by Dr. Michael Pedraza, so professor for EEEI, the title of which is Transmission Planning Process for the SGGP. Paki-flash na lang po yung slide deck. Okay. In fact, this and together with the next 4 presentations, will be related to this planning process here. So, Sir Mike will give the introduction to the series of talks. Sir Mike?
Thank you, Sir Jordan, for the kind introduction. Okay. So, magandang hapon po ulit sa inyong lahat. Again, I'm Michelangelo Pedraza. I am a professor at EEE. And as mentioned, I'll be giving an overview of the transmission planning process of the SGGP, or the Philippines Smart and Green Grid Project. I'll give you an overview of the project, and then in a way, I'll be giving an overview or an introduction of the next 3 talks, which are the components of the project. Okay, so the Philippines Smart and Green Grid Plan, it is an effort of the Department of Energy in collaboration with the National Transmission Corporation to develop the Transmission Development Plan for the Philippines. So this plan is usually developed by the NGCP, National Grid Corporation of the Philippines, and DOE aspires to have its own plan. Okay? And that transmission plan will be integrated as one of the volumes. It's of the Philippine Energy Plan on its 2023 to 2050 update. So what we know is that it will be coming out as one of the 3 volumes of that PEP. Okay, so DOE and Transco are working together, and UP-EEE was tapped as the technical consultants to support them. So aside from developing the transmission plan for the grid, we also have a capacity building component, meaning we're also training the personnel of DOE and Transco such that in the future they'll be able to replicate what we have done. And syempre, we have to work with funds, so USAID comes in as the funding resource. So maraming salamat sa USAID. Okay, so this is how it works. So first I have to define a transmission plan. A transmission plan, it is a plan, it is a schedule of how are we going to expand the current grid. Okay, so population is growing, our energy demand is also growing. It means that the country has to put up more power plants. But we have to move those generators from the plants to the end users, and that is through the transmission network. Okay, so our job is to develop that transmission, to make a plan for that transmission network and how the current grid will evolve such that every year, the grid is adequate. Okay, so every year, generators are coming in, the demand is growing. We want to have high reliability, okay, of the grid. It means that the succession of the addition of projects should ensure delivery of electricity, okay? So this is how the planning process goes, ano? So we receive inputs from the Department of Energy and the National Transmission Corporation, TRANSCO, okay? So DOE usually conducts its capacity expansion plan in the PEP. So when we say capacity expansion plan, it computes or it determines what are the power plants that should be built in the country, what technology should come in, how much. Kaya lang hanggang dun lang siya, no? So we have to do additional modeling and decision-making such that we'll be able to come up with the transmission plan, okay? So DOE also comes up with a demand forecast. So for the Luzon, Visayas, and Mindanao grids, okay? We also get the capacity expansion plan, okay? Now, we also get a base year transmission network model. It's a circuit model of the grid, of the Philippine grid, and it came from TRANSCO, okay? So we're at the middle, we receive that information, we receive that data, and the output is a big document that tells us how the grid should look like by 2050 and how it should evolve from the current state up to 2050. So it includes priority expansion projects, transmission expansion projects, the completion schedule, and the investment cost. Take note that the Department of Energy projects or forecasts several possibilities in terms of the generation portfolio, okay? So usually we have a most likely outcome of the future. They call it the reference scenario. But we have to have a sustainable way, you know, of securing energy in the future. So there are possible scenarios wherein there are massive integration of wind energy in the form of offshore wind and nuclear energy. So we have to come up with a plan that should cater any of those trajectories. Okay, so this is how we approach the transmission planning process, okay? So we have that 2020 grid. That's how the grid looks like right now, okay? And what we do is, in a way, we ride a time-traveling machine. We go to 2050, okay? So, well, DOE gives us an idea what the generators will be, what the demand will be at each area in the network. So we go back, we go to the future, we envision how that grid would look like, okay? So it's a static transmission planning process. So from 2023, we jump to 2050, okay? Later on, I'll give you an idea how we do that jump to the future, okay? Now, once we have an idea of the 2050 grid, now we have an idea, okay, what are the additional transmission lines, the additional transformers that have to be added to the current network. So we have that list of projects. Now, we have to go back, that's number 2, we will now go back to 2030 because from 2023 to 2030, we have to prioritize, we have to identify the projects that should come in that specific area, okay? So from the future, we go back to a future, but a closer future, that's 2030. And we do that by removing some of the projects. So we have this long list, what should be left there, such that by 2030, yung natitirang grid is enough to accommodate the transfer of power. Okay? So that's number 2. And then we're also working with another consultant, Pitera, and they're the one that is translating our analysis in terms of scheduling the project. So they're identifying the years at which each project should come in. So that's the staging process. That's item number 3. And then we are conducting capacity building with the personnel of DOE and TRANSCO such that from 2030 to 2050, they will be the ones who will conduct the staging. So when we say staging, we have to identify what project should come in at specific years. Okay, so this is how we go to the future, how we go to 2050, okay? So the blue box there is the 2020 grid, and in the TDP of the NGCP, there are identified projects na, no? So what we do is we integrate those projects to the current grid, okay? And together with that, we have an idea of the generation portfolio for 2050, the demand by 2050, and then we also have these dispatch scenarios by 2050. The next speakers will tell you about the generation portfolio, the dispatch scenarios, and the DC load flow. So if you have questions on those boxes, please ask them in the next presentations. Okay. So the idea here is that we have a grid. We add the projects. We have the future generators. We have the future demand, and then we will simulate it. And obviously, that grid won't be able to handle the flows. So it will be a deficient or an overloaded network. And the amount of overloading, where that overloading happens, it tells us where to put the additional projects. So we go through a heuristic process of adding projects. What are the transmission lines? What are the transformers that should be added to address and relieve this congestion? So that's the yellow box at the bottom. And then, that grid will be an oversized grid because we want to relieve the congestion. We want to be prudent. We do not want to tell the government that you have to invest these hundreds of billions of pesos for the transmission network. So we reduce the network via optimization such that the remaining grid is just enough by 2050. Okay, so these are the different components. In a way, this is an introduction to the next talks. In fact, to give you an idea how complex the work we are doing. So the first one is generator sizing, siting, and network interconnection to be talked about by Luigi. Essentially, DOE turns over to us the capacity expansion every year, how much generator should come in every year. The work that we have to do is, we have to identify how big those generators are, where to put them, and once we put those generators in their respective areas, how do we connect it to the network? Okay, so it involves a lot of things. The first one, the Philippine map at the upper right, is the renewable energy zones. It tells us where wind and solar should be put up. Okay, the picture at the lower left is the transmission network, the current transmission network. So it tells us, okay, which parts are problematic, where should we add more projects? And then the pictures at the bottom right, we have to go through Google Maps because we have to look for the substations. Usually we just get a list. Nasaan ba yung substation na yan? Saan natin ikakabit yung generator na to? So we have some guys who's just going through Google Maps, looking for those substations and looking at the feasibility of connecting additional transmission lines or transformers in those areas. So again, the details of that, care of Luigi, the next presentation. Now, the next one is the DC load flow. We are evolving a network. We are expanding a network. Siyempre, as electrical engineers, we have to analyze it. And we have to have a circuit model. Okay, we have to have a circuit model. And for the modeling, we used a DC version of the power flow. Okay, it's a mathematical tool that approximates the megawatt flows in the transmission network. Okay, now for this part, that will be care of Adonis, Dr. Tio later on. So if you have questions there, please ask him. Okay, now, the main reason why we use the DC load flow is that it can be used to simulate a deficient network, meaning a network that in reality cannot carry the flows, but still it gives us an idea how and the overload, where they are, where it is happening. Okay, and another advantage of that DC load flow is that it may be integrated with optimization processes. Okay, in MATLAB. Now, from 2050, we have dispatch scenarios pa pala, no? So these dispatch scenarios, it's, well, when you design a network, it should be able to accommodate, it should be able to carry the flows. But when you have a power plant, usually it's off, it's producing at its maximum level. So we have to identify the corner cases. What are the most extreme scenarios? And those extreme scenarios should be able to pass through, or it should be accommodated by the network that we are developing. We have another presentation for that. Si Joshua naman yun. So if you have questions, nasa kanya yung mga math nun. Okay. Now, so from 2050, we go back to 2030. It's just DC load flow. We remove the projects by optimization. We have another guy that's doing that. Now, the plan that we got from DOE, has several scenarios, so we should be able to accommodate that. They call it the clean energy scenarios. Okay, so what we do is we have the 2030 grid, and then we just input or simulate on that the 2030 generators and see if which of the projects should be installed, okay, that can accommodate the three different scenarios. So that's how are we readying the grid such that it is flexible to accommodate the different scenarios. I think this is my last slide. So again, main takeaway dito is that transmission planning is more difficult. It's more complex than generation planning. And the two should have feedback. Ay, nawala na yung slide ko. Sige. Upo na raw ako. But there should be feedback between transmission and generation. And with that, maraming salamat po. Actually, in that slide listed are the personnel, the faculty members, and the students that I'm working with. Maraming salamat po sa inyong lahat.
Thank you, Sir Mike. So we still have a couple of minutes to entertain one or two questions for Sir Mike specifically. And then yung iba pang tanong daw sa susunod na presentation na. Anybody, you can come and approach the microphone at the back. Kahit wala na po, we will award the certificate of appreciation, Sir Mike. But if you still have questions, mamaya, akit ulit Sir Mike to accommodate those. Thank you, Sir Michelangelo Pedraza, for sharing your presentation on the transmission planning process for the SGGP during NEECECON 2024. Thank you. So as Sir Mike mentioned, the next presentation will be delivered by Sir Luigi Tiola. And this will be specifically on the generator sizing, siting, and network interconnection. Siya din yung MC kayo ng umaga, so you already know him. So, Sir Luigi.
Thank you, Sir Jordan. Magandang hapon sa lahat. So today, just piggybacking from Sir Mike's introduction, so I'll talk about generator sizing, siting, and network interconnection. Okay, so if you look at the first volume of the Philippine Energy Plan, it's already published by DOE. So we look at the capacity expansion plan. Ito yung sinasabi ni Sir Mike kanina that the DOE gives us what the generation mix will look like 10 years, 20, 30 years from now. So from this plan, we see that demand quadruples, from around 16.5 gigawatts for the entire Philippines. By 2050, we will be at 68.4 gigawatts. So that's 4 times increase in peak demand. So to cope up with the demand, the DOE projects that we need to add around 122 gigawatts or 122,000 megawatts of power plants by 2050. Okay, so that's around, we're currently at 28.2 gigawatts, so that's almost 5 times more. Okay, so the question really here is, we know, well, the DOE projects what technologies these power plants are, how many, how large, but where do we place them in the network? Okay, so generation expansion planning is basically a process used by energy planners like the DOE and other utilities to find the optimal or the least cost configuration of the power generation. Nawala yung screen. Ayan. Okay, so the optimal power generation mix that meets future demand. Okay, so that's conducted by the DOE, and that's part of the Philippine Energy Plan, as I mentioned. So optimal new capacity is aggregated per technology, okay, meaning X megawatts of natural gas by 2050, we need X number of coal or X number of solar plants by 2050. Okay, and also what's important here is, Sir Mike mentioned earlier that there are multiple scenarios. There are clean energy scenarios where we need to, the DOE tries to simulate what if, or we must adhere to these targets. No? For example, the National Renewable Energy Plan states that by 2030, which is just 6 years from now, we need to have 35% generation coming from renewable energy. Currently, we are at around 22%. Okay? And by 2040, we need to be at 50% renewable energy in the generation mix. So plus, there are also policies like the moratorium on coal power plants, meaning no new coal plants are allowed to enter the grid. And then there are roadmaps for battery storage, offshore wind, and nuclear. So all these policies are integrated into these capacity expansion plans. So to integrate this plan, this capacity expansion plan into the transmission network, we need to disaggregate all these generators. Okay? So this is the general process that we did for generator siting, sizing, and network interconnection. Okay? So if you look at those in color blue, those are from the files from DOE. Okay? So we have the service contracts, the competitive renewable energy zones, most importantly, the capacity expansion plan. So yung nakita niyong graph kanina, that has all the generation mix every year by 2050. And then we take all this data, since the disaggregation of these power plants are spatial or geographical in nature, we leverage the use of GIS, or Geographical Information Systems, which I will discuss earlier. So we site the generators, but before we do that, we need to also size them. Kasi for example, the DOE says, or the capacity expansion plan says, we need 20,000 megawatts of natural gas by 2050. So that's the number they give us. So the question is, where are these natural gas plants need to be placed, and how large are they? Okay? So we need to break them down into unit sizes. And after the generator sizing and siting, then we place these generators in their appropriate places. And then the next step is, of course, they're just generators in a certain area. They need to be interconnected to the network for us to do the transmission expansion planning. Okay, so these are just some maps. So I mentioned the spatial nature of disaggregating technology. So if you see on the leftmost, that's CREZ. That's a study published by NREL with DOE. So Sir Mike talked about this. So this just details where the solar, wind are more probably best located. And then we have also the transmission network from NGCP and Transco. And then on the right, this is a new study published by the World Bank, where best to place offshore wind. Okay, so we see a lot of new areas there, like Northern Mindoro, Southern Mindoro, and Guimaras. Okay, so we need to integrate all these maps into something that we can use to site these generators. Okay, so we start with sizing, kasi of course, as I mentioned, napakalaking capacity expansion plan, it's hard to distribute them. So the capacity expansion plan is aggregated per technology, so we need to break it down to typical units sizes. Okay? So unit capacities will facilitate easier disaggregation of the generators. So we have this list that we coordinated with DOE on what the typical unit sizes are. Okay? Of course, historically, we see different sizes of coal, units of natural gas, but we agreed on a certain typical unit capacity. So for example, if there's 2,000 megawatts of new natural gas to be sited, and we assume that a typical unit size of natural gas is 418 megawatts, then we have around 4.785 units to site all over the grid. Okay, so we can have combinations of 4 by 418 megawatts or 1 by 328 megawatts. Another example is if the capacity expansion plan says we need to have 575 megawatts of new hydro run-of-river, and we assume the typical unit size of hydro ROR is 5 megawatts, so we have 115 units to scatter around the network. Okay? So once we have that number, how many units do we site? How many solar units do we site? How many battery storage units do we site? We need to look at generator siting. So each generation technology has its own set of what we call siting criteria. Okay? So for example, for RE, there's your resource potential, of course, where the wind blows best or where the sun shines best. We also look at already awarded service contracts. Because in the DOE, before you can put up a solar plant or a wind power plant, you need to apply and be granted a service contract. So this list of service contracts that the DOE gave us gives us an idea where the investors want to put up. Of course, before they put in money or apply, some of them already have done their own feasibility studies or resource assessment studies. Another information that we looked at are, for example, for hydro, of course, the priority areas for hydro will be rivers, reservoirs for our dams. Okay? For our conventional, the coal, natural gas, and nuclear, we need cooling. So we need proximity to water. These plants run very hot, they need water for cooling. And also, ports, because most of our fuel is imported. So easier access to ports, to seaports, will allow for better efficiency in logistics. Okay? Another thing that we look at for conventional is just look at where the current power plants are. So we have a lot of them in Bataan for coal, and we have a lot of them for natural gas in Batangas. So maybe that's a good place also to distribute these generators. So every municipality in the Philippines we look at. No? We look at against these criteria, and heuristically we assess them. So for example, one municipality, you see the maps here, this is one of our preliminary outputs. So the colors there are different criteria. So one municipality can tick off 3 criteria in a certain technology. For example, for coal, it might be, that municipality might be near water, might have a seaport, and it might have already an existing coal plant there. So there's a high chance that we can place these new coal units there. So we use a combination of GIS, as mentioned, mapping, and spreadsheet tools to facilitate generator placement. Okay? So once we place the generators or over the network, of course, we need to interconnect them to the grid. Okay? So each new sited generator will be placed in GIS again, and then we overlay the transmission network. Okay? So this is something that we took from what Transco and NGCP had, but we translated it into GIS because there was no readily available GIS form for the transmission network. And one by one, all the generators that we have cited, we need to determine which is the best connection point. So we considered factors such as substation type. No? Hindi necessarily siya yung pinakamalapit na substation, pwede na siyang kumonect doon. Because sometimes, some substations are utility-owned or even generator-owned. And you may already know that the Philippine electric power industry is already privatized. So each substation might have its own owner. Okay? So we also considered voltage level. So for larger generators, we tend to connect them to higher voltages, 230 kilovolts, even 500 kilovolts. And those with lower capacities, we assign to 69 kV and even lower voltages. Okay? So that's the entire process. We repeat that for each grid, for Luzon, for Visayas, for Mindanao. And then we do that again for the other scenarios, the clean energy scenario 1, the clean energy scenario 2. So that's a lot of work that the team is currently doing. Okay, so to summarize, we are given a capacity expansion plan that are aggregate numbers. We size the generators, and then we site them in the network using heuristics, and we use GIS to facilitate this. And then the main output will be the network. Now, the electricity network, for example, by 2050, with all the new generators already connected. This is the sample output. I did not label it for since this project is still ongoing. But you see the transmission network and then the generators where they are sited. So this model will be then forwarded to the next step for the transmission expansion planning. So that is all for my talk. Maraming salamat po.
Again, we welcome questions from the audience. Please feel free to approach the mic at the back. So let us award this certificate of appreciation Mr. Luigi Teola for sharing his presentation on generator sizing, siting, and network interconnection during NEECECON 2024. So for the fourth presentation, which is third in this series, this will be delivered by Justin Joshua Ramos. So he finished his master's in electrical engineering while being a teaching associate at the Institute, and he's now a senior lecturer at the Institute. His presentation is on the development of generator dispatch scenarios for reference and clean energy scenarios. Let's welcome him on the floor.
Hello, mic check. Ayan. So good afternoon, everyone. I am Justin Joshua Ramos. I am a research member of the Smart Grid and Green Plan headed by Sir Pedraza, Sir Jordan, Sir Adonis, and Sir Luigi. And I am here this afternoon to present to you or to carry over what Sir Luigi discussed earlier. And I would like to, before I start, the screen. This presentation will be titled The Development of the Generator Dispatch Scenarios for Reference and Clean Energy Scenarios. So, like mentioned earlier, this will be a series of talks that will carry over from the previous one. So, this talk will carry over from what Sir Luigi discussed earlier. So, the main question I would like to emphasize in this talk is to simply answer a very simple question. So from the generators placed and cited and sized by the methodology discussed by Sir Luigi, we now ask ourselves how much of the generator capacity must be dispatched or how much of that generator is the output for a given scenario by year 2050, by year 2030, or at any particular scenario. So that is that is the main question I would like to address in this short talk given to me this afternoon. So, okay, so now we have a set of generators by year 2050. We placed it at different locations. We provided different sizes, capacities, etc. We now have to know how much of that generator must be scheduled. So it might be a very simple question, but it is quite a complex one because we must understand that there are a lot of scenarios out there. What if it is summer? What if it is evening or noon? These generators that are mainly composed of solar, wind, those variable in nature, they vary depending on time and season. So how can we exactly capture how they will behave at year 2050 provided that we have a lot of scenarios at hand? So in this talk, I will present to you the assumptions, the processes made by the team to make a very good model for these cited generators. But there is one equation located at the top showing that the total generator schedule or the total output of the schedules dispatched must always be equal to the demand by year 2050. And this is important for us to proceed with the power flow analysis that will be discussed by Sir Adonis later on. So, sorry. So this is just a rough methodology of the process. So the input of the dispatch scheduling process is the site and size generators from the previous discussion. And later on, I will show to you this process in which what we call clustering, the second box up there. Because yes, like what Sir Pedraza mentioned earlier, that we want to design a model that can handle the extreme scenarios of the Philippine grid by year 2050. We cannot naively say that, okay, solar generators can always be at the maximum output during summertime. We cannot naively say that solar generators are at zero output during non-summer months. Because we know that, yes, during summer months, solar generators provide high output, but we cannot say that those are equal to the maximum capacity of the solar panels. So we ask the question, the big question of how high is high and how low is low. So that is the part being answered of the VRE clustering process. Beyond that, we try to schedule those generators that are not variable in nature, particularly coal, nat gas, batteries, oil. We try to schedule them by keeping in mind that we must always have an equal demand and generator schedule. And at the end of this discussion, the output will be handed out to multiple power flow analysis methods, in particular the DC power flow method that will be discussed later on. So whenever I say these scenarios, for me to just shed light what a scenario is, so this is just a snippet of the TDP 22 to 2040. So we can see here, I hope it can be read properly. On the first column there, we can see that there are multiple scenarios wherein they try to simulate scenarios wherein we have a maximum north, the north side of Luzon, for example, the maximum south of the Luzon, in which they are trying to say that all generators located at the north of the Luzon or south of the Luzon are at max output. So we can see that there are a lot of scenarios out there. But for the SGGP team, we summarized everything, or we tried to simplify all scenarios into 4 scenarios only. We have here the non-summer evening, the non-summer noon, summer evening, and summer noon. So we see here that we mainly used the difference in time, season in our dispatch cases. So this is one of the process we did to schedule those generators that are variable in nature. This is the clustering process I mentioned earlier, wherein the coordinates determined by the sizing process from the last talk, we use that as an input to get the historical data for solar and wind profiles from different locations in the Philippines. After that, we entered that into our VRE clustering process program developed by the team, in which we try to answer the question how high of the solar generators must be dispatched, how high of the wind generators must be dispatched. Okay? So this is the result of that process. So let me just introduce this plot shown in the screen. So the x-axis or the horizontal axis shows the different solar, wind locations. So that's location 1, location 2, location 3. While the vertical axis or the y-axis shows the generator output. So notice that there are a lot of orange strands out there on the plot. And each of those orange strands right there represent historical solar and wind data from year 2021 to 2022. So each orange strand out there is an hourly data from 2021 to 2022. So what we did is that we determined the best representative scenario or the best representative output for solar and wind out of those thousands of data from those 2 years mentioned earlier. So that technique is what we call the clustering technique, or in a more technical sense, the K-medoids process. So from here, we now try to dispatch the dispatchable generators, namely the coal, natural gas, hydro, etc. And in this table right here, we present the dispatch rules to determine which generators must be prioritized to fill up the demand. So please take note that the list there is presents a hierarchy, meaning we prioritize those that are in level 1. Then we go down as we try to fill up the load. And take note that is not a random order. There is a reason behind it. So for example, the topmost level belongs to solar and wind because we cannot really control the amount of solar and wind outputs. The next one, we see that we dispatch the minimum output of coal and nat gas plants because we have to ensure that in a network, there must always be inertia in the system. We have to ensure that there are actual generators running in the system. So notice that we can go farther down to oil and battery just to fill up the demand. So in the succeeding slides right here, I will just present a simple process, a simple example of how we apply the dispatch rules to fill up a sample demand. In this case, we have here 48 gigawatts of demand at the lowest column. So the first column shows the list of generator technologies. The second column shows an example total capacity of those technologies. The third column shows the actual schedule for that particular generator technology. And the fourth column shows the percent dispatch for that certain generator type. So let's try to go through the hierarchy presented in the table. So the first one, the level 1, shows that we scheduled the solar and wind. So let's try to do that. So as a result of the clustering technique I presented earlier, the results says na, okay, we dispatch 75% of solar, as shown in the fourth column, and 52% of the wind generators, and 100% of the river, run-off river plants. And if we total the outputs at the bottom, it is still at 30 gigawatts. So it is still insufficient to complete the 48 gigawatt demand. So after that, we proceed to the next level, which is level 2, in which case we dispatch the minimum output of our coal and nat gas plants, which is at 30%. So notice that we added there 30% for nat gas and coal, but we see that the total schedule is still insufficient to supply the 48 gigawatt demand. So we proceed farther down the table. So we proceed with the geothermal, hydro, and biomass. So it's still not enough until we reach level 4, in which we try to complete the demand using our coal and nat gas plants. So we see here now we stop at level 4. We no longer have to dispatch oil and battery because we already satisfied the demand. So that is just a quick sample of how we do the dispatch rules, how we schedule the generators, presented by Sir Luigi earlier. And this is now the final result of the process. So if you'll notice along the second column, it is a bunch of bus numbers. But in the project, those are actual Philippine buses. No? So we just replaced the names there. And the other column shows how much of the generators connected at those buses must be dispatched at a particular scenario. So this is now the data that will be transferred to the next presenter, no, Sir Adonis, for the DC power flow analysis. So to summarize everything, what we presented here is that a continuation of the generator sized and cited from the previous talk, wherein we answered how much of those cited generators must be scheduled for a particular scenario, while keeping in mind that the total generation must always be equal to the total demand. We also presented that for us to schedule those generators that are variable in nature, namely solar and wind, we undergo a certain technique called the clustering technique, because we have to know how much, or we have to know how high is high and how low is low. And lastly, dispatch scenarios, dispatch rules, there are a lot of them, no, that can be adapted for any particular scenario. And we presented a one sample process of how we do it in the SGGP project. So with that, I thank everyone for this short time given to me. I hope everyone has a great afternoon. No? Thank you so much, everyone.
Thank you, Joshua. Any question from the floor? Sige, kung wala, Joshua, I'll award to you this certificate of appreciation. Can you start over there? Certificate of appreciation presented to Justin Joshua Ramos for his presentation on development of generator dispatch scenarios for reference in clean energy scenarios, NEECECON 2024. The fifth presentation for this afternoon and the fourth in the series will be delivered by Dr. Adonis Emmanuel Tio, specifically on the DC power flow as a simulation and optimization tool for the SGGP. We welcome him on floor.
Okay. Good afternoon, everyone. So I'm Adonis Emmanuel Tio, and I'm part of the team working on the SGGP. No? So I'll be discussing the DC power flow as a simulation and optimization tool for the project. So essentially, DC power flow is the main tool or process that we use to compute the power flowing in the transmission network. No? And this is an important part of the project because this is what we use to check whether the projects that we add is already sufficient. No? Kung sapat na ba yung transmission lines at transformers na dinagdag. So here's the outline. First, we'll look at the role of power flow in power system planning. Then number 2, we'll look at AC load flow versus DC load flow. And lastly, we'll look at how we use the DC load flow in the project. So like Sir Mike mentioned earlier, power system planning essentially means we want to ensure that there is adequate resources in the future. No? Kasi nga, lumalaki yung demand, yung load, kailangan magtayo ng generator. So yung part na yun yung sinasagot ni DOE. No? Doon sa PEP, gaano karaming generators yung kailangang itayo. So another part of power system planning is to determine how much new transmission lines and substations need to be built. So yun naman yung gustong sagutin doon sa TDP na ginagawa ni NGCP and what we're also doing here in the project. Okay? So ano ba yung gusto nating malaman doon sa power system planning? Of course, doon sa generation side, dapat mas malaki yung installed generation doon sa projected demand. Doon sa transmission side naman, kailangan mag-follow ng grid operating standards, yung transmission grid. So ano bang ibig sabihin nito? So, maraming standards yung kailangan ma-meet ng transmission grid. Number 1, dapat walang prolonged overloaded equipment para hindi uminit at hindi masira yung mga linya and transformers. Number 2, voltage magnitudes near nominal level. So ito yung plus, dapat malapit sa mga outlets natin, dapat 220 volts. No? Sa transmission network, may ganun din. So dapat malapit dun sa mga levels na yun. Yung voltages. Number 3, dapat yung system losses ay acceptable na level. So hindi dapat masyadong malaki para hindi masyadong malaki yung binabayaran natin. And others, safety, reliability, stability, policy targets, and economic operation. No? So maraming iba't ibang standards yung gusto nating ma-meet. Ang covered lang nung power flow analysis itong unang tatlo. No? So with power flow analysis, we can check whether there are overloaded equipment, whether voltage magnitudes are near nominal level, and whether the system losses are acceptable. Okay? So ano ba yung power flow problem? So doon sa mga EEE dito na students natin dati, inaaral natin to no, sa isa nating course. So essentially, power flow is a variation of circuit analysis. When we say circuit analysis, given kanong circuit, which is essentially the grid, given yung connection, yung susceptances or impedances, yung location ng mga supply or generators, tapos yung load, no? And from this circuit, we want to solve for the voltage and voltage angle everywhere. So sa lahat ng node, gusto nating ma-solve yung V and theta, and we know that once we already solve for the voltage and the angles, kaya na nating ma-solve yung ibang parameters ng network, like the current, real power, reactive power, and losses, I squared R. Okay, so essentially circuit analysis yung power flow. And we know, dun sa mga nag-take na nung course natin sa EEE, power flow is modeled as a system of nonlinear equations taken from the power equation, KCL, and Ohm's law. So essentially, you have these equations here for P and Q for all nodes in the system. And you'll see that it is nonlinear, no? Because of the cosine and sine functions and the multiplication of variables. Okay? And because we have a system of nonlinear equations, hindi yun tinuturo usually sa undergrad programs, no? Unless meron ka talagang problem of system of linear equations na na-encounter natin sa power systems. So we know that the solution to the system of nonlinear equations is iterative using Gauss-Seidel or Newton-Raphson. Okay? So AC load flow is accurate and easy to solve for just one state. Kung isang circuit lang yung gusto nating isolve, okay lang siya, mabilis siyang isolve, no? Kahit non-linear system of equation siya. But it gets troublesome if we want to do analysis of many states. Kunwari maraming circuits yung gusto nating isolve. Or kapag yung case natin non-converging state, no? Like what Sir Mike mentioned earlier, paano kung too far into the future yung gusto mong circuit na isolve, pwedeng hindi mag-converge yung AC load flow. Okay? Or troublesome din gamitin yung AC load flow if you want to optimize with power flow constraints. Kasi nga non-linear yung equations na to, mahirap mag-optimize ng non-linear optimization problems. So dito pumapasok yung DC load flow. DC load flow hindi na to tinatackle usually sa undergraduate program unless you're an electrical engineer. DC load flow is an linearization of the full AC load flow model. So from our nonlinear set of equations above, you can simplify it into linear equations na lang. Okay? And usually we drop the equation for the reactive power and we're just left with the linear equations for the real power, yung nakadilaw. Okay? So since this is a linearized model, hindi na iterative yung solution process. And mas mabilis na itong isolve. And you lose some of the accuracy, but it's still accurate enough for transmission networks. And it finds applications in operations and planning. Okay? So the drawback is that it ignores reactive power flows, voltages, and losses. May pros and cons yun, no? Ang pros niya, hindi na natin kailangang problemahin yung voltage, reactive power, and losses doon sa analysis natin. So parang hindi na natin yung problema. Yung problema na lang natin, yung real power flow, kung meron ka bang enough capacity. Of course, the con is, kailangan mo siyang problemahin at a later stage. So kailangan mag-run ka pa rin ng AC load flow later to check for reactive power, voltage, and losses. Okay? So parang first step lang yung DC load flow doon sa solution process. Okay? So paano ginamit yung DC load flow doon sa project? So now, the first step is to build the DC load flow model. So the existing model from Transco is the full AC model, no? So we just convert that to DC load flow by removing some of the parameters, no? And of course, some sanity checking. So nagtagal din yung team dun sa part na to because at the start, we have multiple sets of data and we need to consolidate kung pare-pareho nga ba yung data na yon. Tapos minsan, iba-iba rin yung bus names, no? Iba yung bus name sa data source na to, iba yung bus name sa data source na to, and kailangan pa namin cross-check kung sino nga ba sino. Okay? So medyo nagtagal din kami dito sa pag-build pa lang ng DC load flow model. The next step is to identify dispatch scenario. So matagal din tong gawin, no? Because the first step here is what was discussed by Sir Luigi. You need to disaggregate the generation. Then after nun, pinasa kay Sir Joshua to get the dispatch para meron ka nung power injection dun sa nodes. So matagal na process yon kasi malaki yung grid, maraming bus, and manually siyang chine-check and pinapopulate. Okay? So once you have all the inputs together, we can now run the DC load flow so that we can solve for the power flows in the transmission network. Okay? And we use here a visualization tool that we will also discuss later, no? After running the DC load flow, of course, marami tayong makikitang overloaded na lines. So the next step is to identify candidate projects to try to resolve the overloading. So iterative tong process na to. So mag-isip kami nung additional project from the visualization, then we run DC load flow again to check whether natanggal yung overload. So kung natanggal, good. Kung hindi natanggal, so we iterate, no? We identify more projects until eventually we have a set of projects that removes the overloading in the network. So once we have that set of projects, we now use what we call a DC optimal power flow. So this is an optimization with DC power flow constraints to remove unnecessary projects from the initial candidate list of projects. Okay? And finally, dahil nga DC load flow ito, approximation siya ng AC load flow, we have a final step that have more detailed analysis on the final set of projects. So dito naman papasok yung costing, power quality analysis using AC load flow to check for the voltage, VAR compensation, and potentially other studies, no, like stability, reliability, and short circuit. So whether ma-cover pa namin to sa project or not, we'll see, no? Okay, so the next set of slides are just visualizations. Oops. Pwede pong pa next slide. Yan. So papakita ko lang yung tool na ginamit namin to conduct this load flow. So this is program from MATLAB that one of our team members built from scratch, no? So after attending my course on power system planning, so doon namin pinag-aralan yung DC load flow. So kaya nang gumawa ng script sa MATLAB. So essentially yung input ng script ay yung network data consisting of the bus data and branch data and the dispatch data from Sir Joshua. Okay? So papasok yun doon sa tool. Then, ang output niya, yung power flow dun sa network, sino yung overloaded lines, and ipapasa namin yung results for visualization. Next slide, please. Yan. So, ito yung sample result ng tool. So, may table kami ng overloaded lines and gaano kalaki yung overloading. And we also have a plot of the overloading, no? So, para madaling makita sino yung lagpas na dun sa 100% loading and sino yung marami pang extra capacity. So we plot this using a box and whisker plot. Next slide, please. So this is the visualization naman of the power flows in the network. So we use Gephi, a free graph visualization tool. And we use this in identifying projects, no? Kasi mas madaling mag-visualize ng projects kung alam mo saan yung overloaded na lines. Okay? So using Gephi, mas madali namin nakita saan yung overloads. Next slide, please. And finally, we also have a tool, DCOPF tool, that removes redundant candidate projects. No? So again, this is developed in MATLAB. And again, yung nag-develop nito, kaya niyang gawin yan after taking the course on power system planning. So madali lang siya if you take the course. Okay, so this ends my presentation, and thank you for listening.
Sir Adonis is the fourth from for the series. So kung may tanong kayo on anything about the project, please feel free to ask right now. Anyone? Sige, kung wala nang tanong, we award this Certificate of Appreciation to Sir Adonis. Certificate of Appreciation presented to Adonis Emmanuel Tio for sharing his presentation on the DC power flow as a simulation and optimization tool for the SGGP NEECECON 2024. So we had 4 presentations related to the generation and the transmission planning. The last presentation for this session will be on embedded generators, EGs, integration, the Meralco experience. Our next presenter, Mr. Andrew Charles Young, is the head of the embedded generation integration planning for Meralco. Again, Meralco is a partner of the EEEI. And Doy ang tawag ko sa inyo, Andrew Young, we call him Doy. He's actually graduated DSEE and MNEE from the EEEI as well. So we're proud of him as our alumni. So Doy, take the stage.
Good Good afternoon, everyone. Thank you, Sir Jordan, for the introduction. So, again, good afternoon, everyone. So, my name is Andrew Charles Yang, and I am representing Meralco's Embedded Generation Integration Planning. And today, I'm going to give a short talk on embedded generation integration, the Meralco experience. Okay, so here's a brief outline of my presentation. So I'll start off with the overview of the Meralco system, and then just some definitions of embedded generation and renewable energy, as well as yung particular focus of my presentation, which is variable renewable energy. And I'll also be showing some of the renewable energy solutions that are being offered in Meralco, as well as a simple flowchart of the interconnection process if you wish to apply your embedded generation with Meralco, as well as a snapshot of the embedded RE plans currently in the Meralco franchise. So, okay. So as a brief overview, so Meralco's franchise area covers an area of 9,685 square kilometers. It serves 7.8 million customers as of year end of 2023. The franchise area consists of 39 cities, 72 municipalities, and covers a land area of 3% of the Philippine land area. But within this franchise area of Meralco, it houses 25% of the Philippine population, and the franchise area also caters to 50% of the GDP and contributes 55% of Philippine energy sales. Okay, so now just to describe a paradigm shift that is currently happening in the electric power distribution system. So the facilities shown in the rectangle in the middle, so these represent the facilities in Meralco's distribution system. So we have our delivery point substation, which acts as the transition point between the distribution utility and the NGCP's transmission facilities. And then we also have sub-transmission lines, which conveys power from the NGCP grid towards Meralco's distribution substations, which are located in different load centers across the franchise. And the distribution substations will now convey the power to Meralco customers through our distribution lines and distribution facilities. So in the conventional power distribution system, so bulk power is produced at our bulk generation plant. So that's the square or the rectangle on the upper right, yeah. And then it conveys the power through the transmission facilities to the different DUs covering the country and then serving our customers. So the paradigm shift in recent years is that there is an increased uptake in the integration of embedded generation, particularly VRE in the system. So embedded generations is connected to the distribution system rather than the national grid. And these are connected at either the subtransmission level, directly to distribution substations, or distribution facilities serving our customers. And there is also a subset of embedded generation, which is called net metering, which is connected behind the meter. So that is at the household level. And this has given rise to the what we call prosumers or consumers, which also produce their own power. Okay, so what is embedded generation? So per the PDC, so embedded generators are generating units that are indirectly connected to the grid. So mind you, the grid with the capital G is actually the national grid. And through the distribution utilities lines or industrial generation facilities that are synchronized with the grid. So there are two types of embedded generation. So we have conventional embedded generation and renewable embedded generation. Shown on the bottom of the screen is a simple infographic of our power distribution system. So the area in the hash rectangle is the distribution utility, and the embedded generation, as mentioned before, are ones connected to the subtransmission level, directly to the substation or the distribution facilities, as well as the house level. And these are denoted by the small generation units you see at the bottom, which are connected to the distribution grid by the red wires. So just to give a more fleshed out definition, so here is your block diagram describing our embedded generation as well as the different classifications now as viewed by Meralco. So we have conventional generation. So conventional generations are those that utilize finite fuels as their power source. So these can be coal, gas, or oil. And then we also have renewable generation. So renewable EGs are generators that utilize resources that do not have an upper limit. And these resources are renewable on a regular basis and have a replacement rate that is relatively rapid. So they are virtually unlimited in nature. So in Meralco's definition, so we have renewable EGs, but this can also be classified between non-variable and variable EGs. So the main difference between the non-variable and the variable EGs is the non-variable EGs have direct control over their output. So based on the fuel source. And variable EGs have intermittent or varying output. So I'll just give a brief explanation on the VRE. So what is VRE? So it's a generating facility consisting of one or more generating units where electricity is produced from a source that is renewable or cannot be stored unless you're using a battery or intermittent in nature. So some characteristics of the plant, of a VRE plant, is the variability of its output. So it depends. This is because generally, VRE plants are based on weather dependent on nature. So we have solar, we have wind. So it depends even if there's a clear day, it might not be sunny, it might be cloudy. So the output of a solar plant can vary even on a clear day. And then it's also location constrained or location specific because most of our VRE plants are either solar or wind or run-of-river. So particularly for the run-of-river, so you have to install your plant along the river. And then for wind plants, in order to optimize the maximum output, you have to place them in optimal wind corridors across the country. But the main advantage of VRE plants is they are modular in nature. They are comprised of a combination of a lot of small plants that are grouped together. And in this configuration, they are very scalable if you want to expand your capacity. Okay, so this is a new term that was introduced into our lexicon. The distributed energy resources. So this was brought about by the rules released by the DOE in 2022, Resolution 11, Series of 2022. So distributed energy resources is a subset of VRE. So it's smaller power sources connected to the distribution system or the electric system of the end users that could be aggregated to meet a demand. So they are usually renewable energy systems. They are connected at the house level or at the business facility level. And electricity is generated or managed behind the electric meter. And most of these are, especially in the Meralco environment, are rooftop solar, energy storage or battery energy storage. And on the right, you can see some examples of DER. So we have solar, microwind, biomass, EVs, and run-of-river. So in terms of interconnection of our embedded generation, so we have two types. So as I mentioned, Meralco handles embedded generation. So embedded generation or distributed energy sources, the one in the green rectangle, are connected to the distribution system. And then we have different modes of operations for our embedded generation, which are large exporting, EGs, own use EGs, which offsets one's own consumption, and net metering, which is the mode is you offset your own consumption, but with excess power you can generate to the grid. And then we also have grid-connected generation. So grid-connected generation is connected to the transmission grid or NGCP, and then mostly consist of large generating plants, which are comprising of hundreds of megawatts of capacity. And then since they're connected to the grid, so they're managed by NGCP or the transmission system operator, and they usually supply their power to the grid level. Okay, so these are the types of RE solutions that are present in Meralco right now. So we have they are dependent on the plant's capacity, the point of common coupling or the connection point, as well as the mode of operation. So here is a slight infographic. Later, I'll have a more detailed table to describe yung different solutions. So I'll start off at the bottom, which is net metering. So as I said before, net metering is a solution that is connected behind the meter. So the main objective of this solution is to offset one's own consumption as well as to sell off your excess power to the grid if there's any excess power. So they are connected at low voltage distribution system typically, and they range from 100 kilowatts and below. Then we have exporting DER or exporting distributed energy resources. So in interpretation of the rules set out by the DOE, it's like a expansion or a extension of the net metering program. Whereas the net metering program limits ourselves to capacities below 100 kilowatts. For the exporting DER, it's now from above 100 kilowatts to 1 megawatt. So the mode of operation is the same, offsetting one's own capacity as well as selling off the excess to the grid. And then we also have zero export or own use, DER. So the objective of these is to offset one's own capacity, but will no longer be exporting their power to the grid. And then lastly, we have the large exporting embedded generators. No? So these can be connected to either the distribution level or the subtransmission level. And in Meralco's current environment, they range between 100 kilowatt all the way up to maximum of around 75. Okay, so here's a brief summary of Meralco's RE solution. So as mentioned before, we have net metering and its partner exporting DER. No? So as mentioned, they are both operating on the principle that you can offset your own consumption. And if you have any excess consumption, you can sell it off to the grid. So for net metering, the RE capacity is 100 kilowatts and below. And then for exporting DER, it's above 100 up to a maximum of 1 megawatt. Another main difference between the two, is the ownership of the RE facility. No? So for the net metering, the person who owns the house is usually the person who also owns the RE facility. While for exporting DER, it can be owned by the house owner or it can be owned by a solar installer and operator. For pricing methodology, this is particularly for the exported energy. So for net metering, 100% of your exported energy, if any, is compensable or compensated. And for exporting DER, up to a maximum of 30% of your installed capacity will be compensated. And then in Meralco's case, both net metering and exporting DER are 100% RE. And as per rules, both for net metering and DER, a RE certificate meter is required to be installed at the facility to measure the output of the DRE solution. And then they also have something called the Certificate of Compliance, which is a certificate that is being applied with the ERC. So in order to certify that your plant is already ready for commercial operations and to sell your power to the grid. So in the case of net metering and exporting DER, the validity of this certificate of compliance, which is applied with the ERC, is coterminous with either your net metering agreement or DER agreement, whichever applies. And then for zero export or self-generation facility, so these are the solutions that do not offset your own consumption but do not export to the grid directly. So magka-partner is zero export as well as non-exporting DER. So the main requirement for a non-exporting DER or a zero export facility is that your plant capacity should be below the contracted capacity of your load, just to ensure that there is no excess power being generated into the grid. So everything must be consumed by your own facility. And the main difference between a zero export and non-exporting DER is the second row. So in zero export, the end user is the owner of the facility. So the house owner is also the owner of the solar. For non-exporting DER, it is a requirement that the house owner and the owner of the RE facility are different. Okay? And since they are not exporting to the grid, so our installation of the rec meter is either not required or optional as per our clarification with DRC. And then lastly, we have our large embedded generation. So these are the purely exporting plants. So they can be generally any capacity, but as mentioned before, in the Meralco environment, they are above 100 kilowatts in size. No? And then the RE ownership is owned by the generation company. And then for pricing, actually, there are 4 modes of, or 4 ways where you could sell your power off. No? So there's one is the competitive selection process contract, or what we call PSA, or power supply agreement. The next is you can sell your power to WESM, directly to WESM. And then the third one is you could apply for a FIT rate, or what is currently being implemented is the Green Energy Auction Program. So this is like a fixed rate. So you don't have to be dependent on market forces if you just sell directly to WESM. And the last option is if you have an off-taker or a RES, which will buy your power, your renewable power, in order to sell it off to their portfolio of consumers. Okay? So for embedded generations, it can be RE or non-RE, because we've also had diesel embedded generation in Meralco. And then for installation of rec meter, so it's a must. So Meralco and NGCP will both install a rec meter po, at your facility. However, it is NGCP's meter which is being monitored by IMAP, since they are the metering service provider of IMAP. And then for all 3, zero export, non-exporting DER, as well as embedded generations, the COC validity will be perpetual once given until any material change in your facility is effected. If you upgrade your facility, or if you change your generation, your generators, or you change your inverters. Okay, I have two more slides, so I'll just make it quick na lang po. So here's a simplified process flow of interconnection. If you plan to interconnect your embedded generation facility with Meralco. So we start off with the application. As mentioned by Sir Luigi, I think, that you have to have a service contract with the DOE in order to supply power, no? For your supply power. So if you already have that contract, you can already apply with either the grid or either the DU. If you're going to apply with Meralco, so the customer applicant has to supply all the necessary documentary requirements, as well as accomplish a plant parameter form. And the plant parameters that you submit will be used in our evaluation using our distribution impact study to ensure that your interconnection will not have any adverse effect to the system, as well as a distribution asset study if the interconnection will require the installation of any facilities or extension of facilities by Meralco. And then the primary stipulation before you can implement your project is that you accept the results of the DIS and the DAS, and that you will uphold to comply with all the requirements of the DIS and the DAS. So after the completion of your project, so we move on to step 3. No? Assuming that you already completed your project, it will be subjected to inspection by Meralco, just to ensure that you have complied with all the DIS and DAS requirements. And once complied with, we will go on to do functionality testing to energize your embedded generation, and then move on to a commissioning test, which is required to establish the generator unit capabilities, which will go into the certification that will be used to apply for your certificate of compliance with the ERC. So all the tests, functionality testing and commissioning tests, will be witnessed by Meralco and be performed by the plant. And lastly, for the final energization, so these are more on the documentary requirements, the contracts, as well as the provision of the DU certificate on the generator unit capability, so that you can begin with the parallel operation of your generation facility. So I will be ending my presentation with a brief snapshot of the current embedded generation integration in the Meralco franchise. So as of now, this is as of end of June, we already have around 530 megawatts installed in Meralco. The bulk of it is exporting embedded generation, which comprises around 315 megawatts of power. And then we also have around 130 megawatts of zero export capacity, as well as 85 megawatts of net metering customers. And in the next 5 years, based on current application timelines, we expect to install a total of about 1.5 gigawatts in the next 5 years. So actually, this is my last time. Pasensya na po over time. But I thank you for your time and attention. Thank you.
Thank you very much, Doy. Any questions from the floor? This is our last presentation. You're already having your snacks, so we'll keep it this way. Pwede tayo magtanong kay Andrew. Let's carry on the discussion. Anybody on the floor? Sige, habang nag-iisip na, Doy, may tanong ako.
Yes, sir.
Kita na ng Meralco yung duck curve.
Yes, sir.
How bad? Sige nga. Sige.
Well, in the case of Meralco kasi, sir, malaki po yung demand namin due to scale. So, hindi pa siya ganun kalala. Like, for example, in other jurisdictions, like, for example, sa Australia, where they're already ordering the shutting off of some solar due to overgeneration. So, yun pa.
Projection, how soon will this be an issue?
Well, actually, right now we are being mandated to give a report monthly to the ERC if there are any reductions or significant reductions in our power purchases. But so far, sir, malaya pa ho talaga.
Thank you. Anybody? Anyone else? Sige, si Leo yata to. Sige po. Ano to?
Hi, sir. Good afternoon. Leo po from the UP EEEI. Sir, regarding perhaps the policies of Meralco when it comes to net metering, kasi before we were told that when you will be admitted to the net metering program as long as you don't have the battery storage for your system. Do you have updated policies regarding this, especially for rooftop solar, perhaps residential or office spaces that have battery storage together with solar?
Yeah. Thank you for the question, sir. No? Actually, right now, the Meralco is currently reviewing current policies with regards to integrated solar and in BESS. So as of the moment, the status quo of the policy remains. So it should be a separate BESS muna. So, yun pa. Thank you.
Thank you, sir.
Anyone else? Ako may tanong pa, Doy. Yung second to the last slide, you talked about 1.5 gigawatts in the future.
Yes, sir.
Tama.
That's based on, that's based on our current application timeline. So, pipeline, sorry. Application pipeline.
Hindi ko alam kung secret pa yun, no? Pero may 2 gigawatts daw na binabantayan sa Laguna Lake. Totoo yan?
Actually, yes, sir, tama. That's true. Actually, we were also tasked by DOE to take a look into dun sa mga applications, Laguna Lake, floating solar. However, yun nga, under Meralco's jurisdiction, yung nag-apply po sa Meralco. So, most of them did not fall into the pre-approved areas of the Laguna Lake LLDA. So, yung current application pipeline namin did not fall into that. So, it's a different set po that is being implemented right now.
So on top of that?
Yes. Apa.
Thank you, Andrew. Anybody else? Anyone else? Sige. So we give the certificate of appreciation to Andrew. Sige. Certificate of appreciation is presented to Andrew Charles Yang for sharing his presentation on the Meralco experience on embedded generation integration, NEECECON 2024, signed by Dr. Lou Tria, Director of EEEI. So that ends our session for this afternoon. Sorry, for this first set of presentation. You should be having your snacks by now. we'll carry on with the second set of presentations. That will be technical panel session 4, which will be chaired by Sir Ramon Santos over there. But I hope you appreciate the discussions this afternoon. We started with the future of energy transmission by Sir Ton Ambatali. And then we had a big discussion on generation and transmission planning, but we capped it off with what's happening closer to us with embedded generation. So all of these are contributing to the national development through sustainable industrialization, which is the theme for this conference. So again, thank you very much for joining us this afternoon. And enjoy the rest of the meeting. So I was reminded the next session will start at 3:10, okay? So, but before we leave this room, we once again extend our heartfelt gratitude to Advanced Energy, Techmark Keysight Technologies, Embedded Silicon Technology Solutions Corporation, Meralco, Analog Devices Incorporated, Presidium.ph Corporation, Rhodes Quartz Philippines, Alexan Commercial, Maker Lab, Samsung Electronics Philippines Corporations, and Challenge Systems for their invaluable support to NEECECON 2024. The next set of presentations for TP4, which will start at 3:10, are even more exciting, so we hope that you will come back after the break. Thank you.